All right, this video looks at stoichiometry again. So as we've talked about from the very beginning of our work in the course, stoichiometry is one of those concepts that's super important. And what we're going to do now is we're going to look at stoichiometry involving gases. Now, stoichiometry involving gases, when you're dealing with these gases, it's going to follow the exact same steps that we had. So it's nothing new. The only difference is that we will now have different ways to calculate moles. That's all. So that is sort of the important part here. We've got new methods now to figure out our moles. So if we think about the ways we can calculate moles now when we're dealing with gases, the other weapons we have to find moles is that idea of our molar volume. Now this one, the key is that you're at STP. Okay, you have to be at STP. If you are not at STP, do not use molar volume. Okay, so that has to be at STP. And remember that relationship is 22.4 liters per mole of a gas, right? But the key is that's at STP. That's the only time you can use that, unless you know what the molar volume is at a different set of conditions, but that's unlikely. What more often you'll use is you'll use the ideal gas law, right? You'll use the ideal gas law because it doesn't matter what P, V, or T conditions you have. So remember your ideal gas law is PV equals nRT. And if you want to isolate for n, we divide both sides by RT, so we get PV divided by RT. Right? So that's what we're going to use when we're working through these problems. Now, if you're going to do stoichiometry, right, just remembering what our steps were from our previous work that we did, we had 4 steps, right? Essentially 4 steps when you're dealing with your stoichiometry. The first step was a balanced chemical equation. Doesn't matter what you're working with, any stoichiometry problem, you should be starting with this balanced chemical equation. The second step we had, we called it CTM, that was convert to moles, right? So find moles, that's what you're doing on that step. The third step was your mole ratio. Super important because that's how you relate one chemical quantity to another via its mole ratio. And then the fourth step was to convert to the desired unit, right? So that could be a mass unit, could be a volume of a gas, it could be the volume of a solution, it could be concentration, number of particles. There's lots of options, right? We have lots of different units we can express things in. So the last step is to convert it to whatever particular piece you need. Now, one other piece to remember when we were doing stoichiometry is you could also have a limiting reactant, right? And a limiting reactant, we still have to consider that when we're dealing with gas stoichiometry, right? So you have to consider if a limiting reactant is needed. Okay, so, and if you can't remember how you can tell, if they give you information about more than one reactant, if you're able to calculate moles of more than one reactant from the data given, then you need to consider which of those 2 reactants would be the one that runs out first. Because as soon as one of those reactants runs out, nothing else can be made, right? So if you are in that scenario where you've got information about multiple reactants, enough you can figure out moles initially of both, then you have to consider it as a limiting reactant problem, right? And do the mole ratio with each to figure out which produces less of the product, right? So those are your steps to a stoichiometry problem like we saw before. And now we're going to do a problem using gases in that particular stoichiometry. So let's try this example. So this problem says consider the complete combustion of ethene gas. Oh, and I've got a little typo in my ethene gas. Oops. That should be C2H4. If 450 mils of oxygen gas at 107.3 kPa and 27 degrees Celsius is used to completely react all of the ethene, the first thing we want to do is determine the mass of the ethene gas combusted, and then the second part of this problem asks us to determine the volume of ethene gas at STP that was used. Okay, so let's work through this problem and try to figure it out here. And again, like any stoichiometry problem, let's start with what we know and write our balanced chemical equation. That's our first kick at the can here. So step one, for this is letter A that we're working through, we want to write our chemical equation. So we've got C2H4 gas plus O2 gas produces CO2. It's a combustion reaction. It says it's complete combustion. So we're going to get CO2 gas and we're going to get water vapor. All right, so there's our reaction. Now we've got to balance it. And to balance it, if I were to work through this, I am likely going to see that I'm going to need to get 2 carbons here, and then 2 hydrogens there. That gives me enough that I can probably do a little bit of work here, right? So let's check out how this will go. So if I'm going to put my 2 for my CO2 and my 2 for my H2O, that gives me 4 hydrogens, 2 carbons. That is 2 oxygens plus 4 oxygens. So that's going to be 6 oxygens. And I've got O2 here, so I just need my ratio to match. So there's my 6 oxygens. So here's my balanced chemical equation. Now, once I got my balanced chemical equation, C2H4, so I'll just double check. 2 carbons, yep. 4 hydrogens, awesome. 6 oxygens, 4 plus 2, 6 oxygens, we're good. So I got my balanced chemical equation, I'm all set. Now I'm just going to write down some information that I need to find and that I have in the question. So I'm looking for this mass of ethene gas. I know the molar mass of my ethene gas is 28.06 grams per mole. And that comes from my periodic table. And the moles, I don't know. We're going to have to find that. My oxygen, I know the volume is 450 mils. But any calculation I do, I want it in liters. So if I divide by 1,000, I get my quantity now converted to liters. The pressure is already given in kPa, so that's good, 107.3 kPa. The temperature is 27 degrees Celsius. And then if we add 273 Kelvin, that would be 300 Kelvin. So from Celsius to Kelvin, we've done that conversion. And now I've got enough info, I'll be able to find moles. And once I have moles of the oxygen, I can find moles of the ethene using the mole ratio, and then we're good to go. We're off to the races. So step 2 now, let's convert to moles. So we're going to work with the oxygen. So we're going to use PV equals nRT, our ideal gas law. It's probably the easiest way to do it. So when we rearrange to isolate N, we're going to get PV divided by RT. And now we just sub in those values. So 107.3. The volume is 0.45. R 8.314. That's a 4, by the way. And the temperature is 300 Kelvin. So our number of moles then is 0.0193589 moles. So now I know our moles of oxygen. Notice I'm not worrying about significant digits right now. I kept a lot of extra digits. I know that when I look at this work, the Kelvin value has 3 significant digits, the volume has 3 significant digits, the kPa had 4, the ideal gas constant had 4. So we're going to be looking at 3 significant digits on my answer here. And if you're wondering why that is, remember that your temperature, when you add 273, it's all about precision. It's about decimal places. This has no decimal places, so my answer in Kelvin has no decimal places. That now has introduced another significant digit by doing that, okay? So that's why we go from having 2 there to ending up with 3 when it's in a Kelvin value. So we've got our moles. The next step now is to do the mole ratio. So for my mole ratio, I want to find number of moles of C2H4, and I know that's just the number of moles of oxygen times my conversion factor, which is the ratio in the balanced chemical equation. So I want moles of ethene on top, of C2H4 on top, and I'm trying to get rid of moles of oxygen, so it's going to go on the bottom, and I look at my ratio in my balanced chemical equation. It's a 1 for C2H4, it's a 3 for oxygen, so this is going to be a 1, this is going to be a 3, and now I can do that math. I take my 0.0193589 and I'm going to multiply it by 1/3. And when I do that math, just bear with me while I punch it into my calculator, we will get 0.0064529. 67 moles. So that's our moles of ethene, sorry. Okay. And once we've got our moles of ethene, then we are going to find our last step, which would be to convert to the desired unit, which in this case is mass, right? So part A is asking for the mass. So to find the mass, it's moles times molar mass. So 0.006452967 times 28.06, and our mass then is going to be 0.18107, but we want 3 significant digits, so 0.181 grams. So that's our mass of our gas, and that first part of the problem is done. Now, to take a look at the second part of the problem, part B, asks us to determine the volume of ethene gas at STP that was used. So essentially all we need to do now is take these moles of ethene, and we have to convert from moles of ethene into a volume at STP. So I'm just going to move this up a bit. So it's still the same reaction. I'm just going to, my mouse is being silly here. So for part B now, to find the volume, of C2H4, remember that we can use ideal gas law to do this, or because it's at STP, we could also use molar volume. I think for this question, I'll probably just stick with the ideal gas law. That way you know what to do no matter what the conditions are. So if I take a look, ideal gas law, PV equals nRT. I'm trying to find volume, so that's going to be nRT divided by P. And our n value we have, it was right up here, so 0.0064529 67, and the R value is 8.314, and the temperature at STP is 273, right? And I'll just remind you, STP means that temp is 273 Kelvin, and the pressure is 101.3 kPa, right? So I'm going to divide by 101.3, and when we solve for the volume, we will get, so let me just punch that into my calculator. We will get 0.14458 liters. And a more respectable way to talk about this then would likely be in milliliters. So from significant digits, we're still keeping 3 significant digits. That's what's carried in my moles and my Kelvin value. So this would be 146 milliliters. So that would be the volume. So that's doing it using the ideal gas law. If you want, I can quickly show you what you would do if you wanted to use molar volume. Okay, so if you wanted to use molar volume, remember that you can only use this when you're at STP, right? You can only use this idea when you're at STP. So for this problem, because they want the gas at STP, this works for us. So if we take 22.4 liters in a mole, that's the molar volume. That's a formula then to find this would be volume divided by moles, right? So if I want to solve for volume then, my volume would just equal 22.4 liters per mole times the number of moles that I have. So when I'm doing this, I would get 22.4 times 0.006452967. And when we punch that into our calculator, so you'll get an answer in liters of 0.14454 6 liters. So then again, converting to milliliters, we would get 145 milliliters. And that would be how you would solve that problem using molar volume. Okay, and again, it's to 3 significant digits. Now, the funny thing is, if you look at these two answers, you'll probably notice that these two answers for volume are just slightly different. That's because when we get a volume, this molar volume of 22.4 liters, remember this has been rounded, right? It's not perfectly 22.4. So again, and over here, our ideal gas constant is rounded. So there's rounding taking place in these that influence my calculation. So sometimes you might see them, if you do them either way, be identical, or they'll be really close to each other, okay? If you're way off, if you're more than a milliliter or two off, then you've probably done something wrong. But no matter which way you do it, if you follow the steps, you should be able to get the correct answer. Just watch though, you can only use molar volume at STP. This 22.4 liters per mole is only at STP, okay? We could use it because this particular question wanted us to find the volume of that gas at STP. So that's how we do a stoichiometry problem. I showed you quite a bit of stoichiometry there, actually. So we've done our mole ratio up in here, right? So we converted to moles, did our mole ratio, found the mass, and then if we had B as its own problem, you would do the same first three steps, but then it would be the converting at the end instead to find volume. So either using that ideal gas law when you're dealing with the gas, or if you're at STP, you could do it using molar volume. So hopefully you enjoy some stoichiometry with gases. It should be a blast, and good luck with the practice.